Okay, so students, we are going to start a class. I hope all of you have joined. Let's see the WhatsApp there. What's happening? So soon we are going to start the class, okay? I think all of you have joined, isn't it? So please, all of you join here. Okay. So my job is to start. So I'm starting the class. Fine. So students, today we'll start with this wave optics. Okay. Let us see on the WhatsApp how many students have joined there. So if I on it, this is Avanti Live 13. Okay. Let us start it without wasting the time. Okay. Fine. Everything is working. So we were on the wave optics, no, previous class, isn't it? Yes. So see how to start the things. This is our chapter. As you all know, we need to first we'll go through the recall. Okay. Okay. Huygens theory. So in the previous class, we studied this topic first. So this is what learning objectives, contents of this chapter, that is wave optics. So first we studied Huygens theory. Then we studied interference. I mean, we haven't studied, but we have to study. Then what? Diffraction. Then polarization. Okay. So this is Huygens theory. What does it explains? See, let us see the history about this. Let us see somewhat about the history. Again, okay, so in 1637, I told you already, there was one scientist, Descartes. He has given the corpuscles model of light. Corpuscular, what's that? Corpuscular means what? Light as an energy particles. That theory he has given. Okay. After that, he also used this corpuscular model of light. That is his theory of corpuscular model, that light as an energy particles. To explain this phenomenon of reflection and what refraction. Then after 1637, it was the year of 1672 that one scientist came whose name was Isaac Newton. Actually, we know he's very famous scientist, Isaac Newton. Okay. He was one of the colleges of Alva Edison. Okay. So Isaac Newton was a scientist. He has founded what? Actually, he was famous for his work in classical mechanics. We have seen this thing in the previous class. Okay, leave it. So then he also used that model of corpuscular model of light. Okay, so one of the students have joined. Anshu have joined. Anshu, welcome to today's class. Okay, I hope I'm audible to you. I hope I'm audible to you properly. Okay. Okay, I'm launching a poll for you because you are the first student here. I'm launching a poll for you. Please participate in this technical checkup. I'm audible. I'm audible. Click on the yes or no. Poll has been launched. Click I'm audible or not. I clicked yes, yes. Okay, very good. So Anshu, you can also click here. I'm audible. Just participate on the poll. On the left, on the right corner, it will be appearing in your phone. Click on the button yes, audible. And are the slides properly visible to you? So it's if it's yes, then click there on the yes. Okay, I'm ending the poll. This is corpuscular model of light. Isaac Newton, after the discovery of this model of light in 1637, good, Ganshu, good. So in 1637, after the discovery of corpuscular model of light by Descartes, in 1672 came Isaac Newton. He also explained the corpuscular model of light, okay, but he modified it somewhat more. He had done some modification. He did some modification in this model of light. And he also gave a journal, a paper of his information research based on this topic of optics. Again, show no issues. Just focus it. Okay. If you're not able to chat, no problem. Okay. Let's be focused, but please be focused here. Fine. Okay. I mean, oh, that's fine. Okay. So maybe some students are with you, joining with you, na? Okay. So that's fine, sir. Okay. That's fine. Okay. So I'm progressing towards the next. In 1678, Christian Huygens, okay, he was a scientist who has actually given the wave theory of light. So he gave what? He gave the wave theory of light. And according to his theory, he was able to explain some phenomena of what? Actually, we have seen this thing in the previous class, interference and diffraction. Okay. Then in 1801, this is as a revision part because one day we were absent. No, Thomas Young. So actually he did a lot of work. Okay. He, by his theory, explained properly this interference experiment. Okay. So it's better if we include this interference not in that point, but in this point. Actually, its origination started from the wave theory only, but Thomas Young was the first scientist properly. He was precisely able to explain the interference experiment here. Okay. Now let us see the failures of Newton's corpuscle theory. The failure was this. It was a big failure, by the way. What happened is this, and Newton assumed that light travels faster in the denser medium than in the rarer medium, okay, which was proved wrong. Because we already know, and thought like many times in the previous class, we have seen this thing. What we have seen, and that suppose this is a denser medium. And suppose on the other side, this is a rarer medium. If light is traveling like this from a denser medium, say angle of incidence to the rarer medium, it will bend away from the normal. And understand this thing, the speed of light, if here is something, say V1, and the speed of light here is say V2. So we'll call here V2 is greater than the V1. Remember these points. Okay. But here Newton assumed this thing that the light travels faster in the denser medium. Light travels faster in the denser medium. What does it mean? Matlab, it is a wrong assumption, no, because we know this thing V2 is greater than V1. That as light enters from the denser to the rarer, its speed increases. Okay. Corpuscular theory. So actually, Newton's corpuscular theory was not able to explain the phenomenon of diffraction, interference, and polarization of light. Remember this thing. And JNV Damtri students, you have also joined that school. Okay. So we are just discussing here Newton's corpuscular theory failures. Okay. After this, we have studied about geometrical optics somewhat in the previous classes, and then wave optics somewhat. So there was a contradiction. The wave optics conclusion was this, that the light does not travel in the straight line. Okay. for this condition, that size of the obstacle in the path of the light is in the order of the wavelength of the light. Okay, so whatever the obstacle is there, suppose some slit or some gap in the cardboard, if its dimensions are what? Its dimensions are in the order of the wavelength of the light used, then we'll say the light does not travel in the straight line. Okay. And in the geometrical optics thing, it was this, that the light was assumed to be traveled approximately in the straight line. So both of these conclusions, that is, one is here in the geometrical optics. Okay. Here in the geometrical optics and here in the wave optics, if you see, this is, if it says it travels in the straight line, it says it does not travel in the straight line. So these are contradictions. Okay, got it. So today I'm not like very fast because some students wanted to be very slow in this class. Okay. So this was the picture we concluded. Now then we are studying the Huygens theory. We have seen this animation. Let us see one more time again. So this is the top view. Oh, sorry, the side. It's the top view of the water falling from a tap, drop by drop. You can see the circular concentric circles which are appearing, but are nothing but the vibrations. Okay. Same is the analogy we'll use for a light. Okay. So this is a side view here. And side view is explaining you that the waves are like going like this, you know, isn't it? So now let us see the next thing. Yeah. So as I told that if you put or if you throw a rock in the pond, okay, or a stone in a pond or a water tank, circular kind of ripples are generated, and these perpendiculars to that locus of the point that is circled there gives you the direction of the wave. So actually you will say energy wave is traveling like this. Okay. This is a direction of the traveling energy. Actually, I tell you, this is the direction of the traveling energy. This is what? This is the direction of the traveling energy. Down. And this is perpendicular to this green circle. And circle is what? Circle is the locus of all those points I'm writing here. This circle, any of the circle, but here it is marked with the green ring. See, circle are all the circles are concentric, but here it is shown for you for explanation. It's been marked with the green color band here, green color ring here. So we say here like this, circle is what? Circle is the locus of all such points which are in phase. Okay. So at this it's perpendicular, this perpendicular, this perpendicular. So direction of this gives you the direction of the energy wave. Understood? Next is this. Locus of the points which oscillate in same phase is called as wavefront. Remember this point also. Locus of the points which oscillate in the same phase is known as what? Wavefront. Okay. Which we've now only seen. And see, it says light rays always travel in the perpendicular direction to the plane of the wavefront. This also we have seen. And if we see the direction of the energy wave, of course, it's at all the points, it's perpendicular to that individual points on the particular circle or wavefronts. This will give you the direction of the traveling energy here. It's here, it's here. Okay. This also we have seen. So after this, this is the speed of the wave actually. So speed with which the wavefront moves outward, or you can say, suppose you mark the radius of a particular wavefront. And if the radius rate, if you know that dr by dt is what? It's nothing but the magnitude of the speed of the wave. Okay. Rate of change of radius also you can call like what? Speed of the wave. Okay. But here the definition says us that speed with which the wavefront moves outwards from the source is called the speed of the wave here. Okay. After this, we have we talked about different kind of wavefronts. This was a spherical wavefront. I'm launching the video here. Okay, we'll just see the video. We'll not talk about a lot on these points. Okay, so you can see this how that curved kind of lines are going. These curved kind of lines are nothing but the direction of the energy wave. And concentric spheres which are being shown here are what? These are circle. These are spherical wavefronts. Okay. Next, let us see the plane wavefront. So if you take an ds part on the surface of this sphere zoomed here, okay. When I take this ds part, let us take ds parts. And then if you focus on the ds parts, this will give you the planar wavefronts. These are the ds parts from the spheres. Okay. So these are the parts on the spherical wavefronts there. Okay. So these are known as plane wavefronts. See, small portion of the sphere can be considered as a plane. So these wavefronts are known as plane wavefronts. So if you're in this sphere, the concentric spheres, small portion of those spheres can be considered as wavefronts, and these are known as like what? Plane wavefronts. Remember, okay? Yeah. So these all things were completed in the previous class, by the way. Okay, we have already completed these all things in the previous class. So now we'll see the Huygens principle properly. So in the previous class, we have seen the definitions. What were these definitions? Okay. So it says like this, that each point on the wavefront acts as a fresh source of disturbance of light. Okay. Second point is this, that new wavefront at any time later is obtained by taking the forward envelope of all secondary wavelets at that time. Remember this also. So we have seen the demonstration also. It was like this. Suppose this is a source of light and this arrow is showing the speed of the wave. This arrow shows the speed of the wave. What is this arrow showing to you? It shows the speed of the wave. And this is nothing but the wavefront. I can write like this. This is the wavefront drawn. This is a wavefront drawn at time equals to 0. So at a time, so the first postulate of this, or you can say first assumption of this Huygens principle is this, that if you mark some points on this wavefront at time 0, these points, or see locus of the points, if you connect, it will be this wavefront, that's fine. But if you mark these points on the wavefront, these points by itself, by themselves, they'll produce the secondary disturbance. Similar in what? Similar in the looks as it is. This is the main wavefront is, okay. So you can see the main wavefront looks like a semicircle. Similar to this, the points on this semicircle will produce a secondary disturbance, which also looks like this main single wavefront on which these points are like the secondary vibrations, and this will be also like circular, semicircular kind. Okay, and you can see this here. If I show you, so this will be generated. Now you can see it is a complete wavefront is generated, and the source, the epicenter is this. The center of this vibration, the source of this vibration are these points. Okay. Now what happens that at time equals to tau, if it is reached up to this, so we'll say we know distance upon time is equals to the speed. So if you need to find the distance traveled by particular energy vibration or energy wave or vibration, you'll say it is Vt. Here the time is given as tau. So this is the x traveled by this secondary vibration. You can say it's the radius of this small radius. It's all are symmetric. All will be having r equals to V tau only. When I connect the periphery of this secondary vibrations, so you're getting this. So this is now on main wavefront. If you connect the periphery, this will give you the main wavefront here. Okay. So initial wavefront was this at time 0, at time equals to tau. This is the main wavefront. So this was the principle. It says that if you connect the periphery, this will give you the new wavefront. That is also spherical. For the plane, it is like this. Suppose you're having a planar source kind of, okay, and all its point will generate again the secondary vibrations like this. If I launch it, see here carefully. And if I connect the peripheries on both of the sides, see here also and here also. Okay, so what's going to happen? A secondary, if you connect on both of the sides, what will happen? A secondary planar wavefront will appear. Okay, this is what this is among the planar wavefront. So just see carefully. This is spherical wavefront. This is spherical wavefront. This is planar wavefront. So through this in the previous class also we have seen that the types of wavefronts, starting from circular looking like wavefronts, then spherical wavefront, then circular, spherical, then what at the last, what planar wavefront. Okay. Okay, so see, focus here, students. Now, next comes this, that is refraction and reflection by Huygens principle. Okay, so new students have joined, so be focused here. We are starting now. Recall portion is completed. Okay, a revision of the class like day before yesterday, it was over now. It's over now. Okay, so now we'll see a new topic, that is, write this heading in your notebooks. This is refraction and reflection by Huygens principle. We pronounce it as like what? So many times I've told it's Huygens principle. Okay. Okay, let us discuss first what is refraction. Suppose you are having a medium, a boundary which is separating two mediums. Okay, that is, one is having refractive index n1 and other is having refractive index n2. Okay, and suppose n2 is greater than n1, it means what? That the medium which is corresponding to this n2 is what? A denser medium, and medium which is corresponding to this n1 is what? Rarer medium. And we have seen what happens in the refraction process. In the refraction process, this happens, that is, if the rays entering from this denser medium to a rarer medium, it will bend away from the normal, such that if these are IR, we'll say angle R will be greater than angle I. Okay. And next is this. If this is N1, this is N2. Okay. So we'll say like this, that if the rays entering from, say, a rarer medium to a denser medium. Okay. So here, if this is R, this is I, I'll comment like this. If the ray enters from a rarer medium to a denser medium, it will bend towards the normal, such that I is now greater than R here. Okay. These were the two simple cases, very beginning, like simple cases of what? Refraction. The next is this reflection. What does the reflection says? We have seen this thing, if we are having a plane surface. Audible? No. Yes. If you are having the plane surface, see, if any one of you is feeling any doubt, you can reply in the chat box. Suppose you're having the plane surface, and this is the point of incidence here. Okay. So this is angle I, this is angle R. This is known as incident ray. This is nothing but the incident ray. Okay. And the next, this is, we know it is what? Reflected ray. This, I'm talking about the laws of reflection somewhat, before seeing how Huygens principle explains this laws, that is laws of refraction and reflection. This is the angle of incidence. This is the angle of refraction. This is the normal to the point of incidence. Okay. We know the two laws corresponding to it. Basic laws are what? That I ray, that is incident ray, that is reflected ray, and normal to the point of incidence all lie in the same plane. Okay. And second is this, that is angle of incidence is equals to the angle of reflection. This is also a point now. Remember it, okay? So now let us see. Okay, so what Huygens did is what? First of all, let us see how by using his principle, the reflection by light waves can be explained. So he took a boundary XY which separates two medium. This is rarer and denser, okay? Then again, he used all those wavefronts thing and tried to explain it. Okay, we have seen these things on the previous class. Okay, so ultimately, what we have seen the formula derived by him. This was the formula, hold on. That in this, he has given this formula which says sin I upon sin R is equals to the V1 upon V2 equals to N2 upon N1, okay? Where V1 is the speed of the light wave in first medium. It is the speed of the light wave. Speed of light wave in first medium. And V2 is what? V2 is the speed of the light wave in second medium, okay? N2 is the corresponding refractive index of second medium. N1 is the corresponding refractive index of the first medium. I is the angle of incidence in the first medium. R is the angle of refraction in the second medium. Fine? Okay. Now see this carefully. This also was derived by this Huygens. What is this? Lambda 1 upon lambda 2. This is frequency V by lambda is constant. Okay. Remember all these points. So let us move fast now because this we have seen already. And next we have seen the reflection also. And through reflection, he was able to explain the laws of reflection. What does it say? That angle of I is equals to the angle of reflection. Okay. Laws of reflection and refraction is same as in the ray optics. So the behavior of the prism, lenses, and mirrors will be same in the ray optics also. Okay. So here it completes your all the parts. Now we were at this, that to see the behavior of the wavefronts after reflection or refraction. Okay. So see in front of you, this is concave mirror. Check. This is AB incident wavefront. This is CD reflected wavefront. This is convex mirror. These things also we have seen. So what is happening here? Suppose rays are coming parallel like this in a convex mirror. Let us switch back to the concave mirror. So in concave mirror, suppose the rays are coming parallel like this. Okay. This is AB. This is what some other thing. Okay. Rays are coming like this. This is the wavefront. After striking it, it will reach here. Okay, at O point here. Okay. This AB is the incident wavefront. This CD is the reflected wavefront. And see, this is the convex mirror. What is happening in this? Suppose AB is the incident wavefront. CD is the reflected wavefront. Okay. See, wavefronts are not by themselves. Okay. What is happening? We draw a ray diagram and we know in the convex mirror what happens. When the ray passes through the convex mirror, the image formed is what? Virtual layer in this sense. Okay. So we are treating this object to be like a source, a virtual source here. Okay. This is what? Nothing as like, it's just simple a virtual source. And the wavefronts are generated like this. Like this. And it reaches here. Next, let us see for the convex lens. See, we know this is what looking like a biconvex lens. This is just a simple ray diagram of a biconvex lens. You know, we have seen this thing, no? That if the rays are coming parallel on one side, after passing through this biconvex lens, this is something which is biconvex. lens. So on the other side, it will get like this, concentrate at a point. Okay. And if you see the wavefront picture in this, so wavefront picture is like this, a planar wavefront. And after, when this planar wavefront passes through this convex lens, remember what is happening. The initial one is the ray picture. Now this is what? Wavefront picture. So in the wavefront picture, it is explaining us that when this AB wavefront passes like this through the lens, on the other side, it will show you this diagram. Okay. So this is how the wavefront changes. I mean, it was planar. Now it becomes like spherical or circular. Okay. You can see the change. The planar wavefront passed to the lens. On the other side, it is now circular or spherical wavefront. Concave lens is this. So when the rays are coming like this, it passes through like this. Okay. And if you extend the rays back, object is this. And finally, you'll see here, this is the AB wavefront. This is the wavefront here. And when this wavefront passes through this, it's actually biconcave lens. Okay. You will call it as like biconcave lens. It's a concave, it's convex. So when the wavefront passes through this, on the other side, it will appear like this. Okay. On the other side, it will appear like this. Is it clear? Please reply in the chat box. See, nothing is to understand. Just remember the points. Ray diagram, we have seen how the ray diagram is like when the rays are passing from an object. Suppose the rays are coming from infinite, parallel to the principal axis. And on the other side, it gets like merged at a single point, okay, concentrated at a single point in case of biconvex lens. But here, if you see the wavefront picture, the planar wavefront, see, we know if ray diagram is like this, it showed that the wavefront will be straight, like planar wavefront. Why? Because this direction is showing you the energy wave direction or the waves direction, basically. So we can predict from this, if the wave direction is like this, shown by the ray diagram, the wavefront will be perpendicular to it because both of them are perpendicular to each other. Okay. So wavefront reaches here. After passing through this biconvex lens, what happens? On the other side, it will show you this picture. It looks like circular spherical wavefront. Same you can see in this concave lens. Up to this, is it clear? Please reply in the chat box. Up to this, please reply in the chat box. Okay. So I hope you have written this thing. Okay, let me raise this annotations from here. I'm removing the annotations. Hold on. I have removed the annotations. You can now note it down. Okay. Annotations are already removed. So just focus on the wavefront behavior here. That initially it was the planar, it's changed. This is planar, it's changed. Okay. Got it? This is AB incident wavefront. CD is what? The refracted wavefront. Remember this also. AB is what? It's the incident wavefront, and CD is what? Refracted. See, in both the case, it is same. The incident wavefront reaching on the left side of this biconvex lens after refraction has been shown like this. This is refracted. Same AB incident wavefront after reaching the left side of this biconvex lens. On the right side, it's shown by the CD refracted wavefront, but different. So here it's like minimized. It's like made smaller in size with curved. The nature is curved and made smaller in size. Here the nature is curved, that's fine, but it's like you can see it's being magnified. So remember these points. Okay, now let us see how the wavefront behaves, or what is the wavefront picture when the ray is passing from the prism. We know in the prism, when the ray passes the white light, it gets divided into what? It constitutes 7 colors with VIGYAN. Dispersion of light, we say it is what? The prism shows dispersion. Prism shows what? Dispersion. So see, this light is coming. After passing through the prism, you can see how it gets turned. So it was the incident ray. This is emergent ray. I'll call like this. This is what? Incident ray. This is incident ray. This is what? This is emergent ray. Okay, incident, emergent. And internal, what is happening? Internal is the refracted ray. This will call as what? A refracted ray. Refracted ray, refracted ray. See, now you are able to clearly see on the slides what is the wavefront picture here. Okay. I mean, if this is the wave direction, see, ray direction is giving you what? Ray direction is giving you the wave direction. So here the ray direction is giving you the wave direction. Okay. Again, ray direction, wave direction, wave direction, wave direction, wave direction. And we know the direction of the wave is shown by what? Like a perpendicular to the wavefront. So if I join all the points in continuity with the direction, I'll get a plane thing. It means the wavefront is what kind of? Is it circular, spherical, or planar? We can say it's a planar wavefront. And now the wavefront picture is in front of you on your screens in this prism case. So you can see here, when the wavefront passes, this is known as what? AB is what? Incident wavefront. CD is what? Refracted, emergent wavefront. Okay. So you can see here, this will be the picture. This is a 3D view given to you. Okay. It's incident wavefront, incident wavefront. That is refracted wavefront. That is refracted wavefront. This is incident wavefront. That is refracted wavefront. Okay. AB is the incident wavefront. CD is the refracted wavefront. So up to here, is it clear? Please reply in the chat box first. Please reply in the chat box. Are all these points clear to you? See, on the left hand side, it's given the 2D view of the wavefront AB and CD refracted wavefront. Okay, there in the left hand side, it's shown like what? 2D representation, paper pen representation. But on the right hand side, it's been shown by the 3D structure purely. So the blue violet arrows on the right hand side, let me show you here. Okay, I'm highlighting with the laser pointer. So it's in front of you on your screen. So these are the arrows. This is nothing but the incident wave direction. And this is the emergent wave direction. Hai? And the perpendicular to it in the 3D structure, you can see it's shown like a cardboard thing, which is perpendicular to these arrows, both on the left side of this prism and the right side. I mean, on the front face, on the back face. So this cardboard kind of thing is like the incident wavefront, and that cardboard kind of thing is what? Refracted wavefront. I hope it's clear now. Please reply in the chat box, okay? And if you're having doubts, that also I want, because the next part is interference. We can start in the last 5 minutes somewhat. I can give you the overview of the interference. So for that, please reply in the chat box. Up to here, is it clear or not? Because, you know, if it's not clear, then what's the use of starting the next thing? Okay. So I'm waiting for your replies. 2 minutes for all of you. Please reply in the chat box. Okay, so some of the students have replied. That's fine. So you see what? Yes, sir. Okay, fine. So we'll start. We'll see an overview of the interference. Okay, we'll not complete it, but we'll see an overview so that in the next class it will be easy for us to begin to start. Okay. I hope the slides are properly visible on your screens. Is the slide properly visible? Okay, write the heading interference. You know, in the history of this previous wave optics, I mean the first slide, we got to know about one person, famous physicist. What was the name? His name was Thomas Young. His name was Thomas Young. है ना? So he actually explained properly about interference by using the wave theory of light. Now we'll see that. So these are the learning objectives. I mean the contents. First, we'll go through the introduction to interference. Okay, we'll understand what is this interference is, okay, and how it looks, what are the animations, how practical it looks. All these things we'll see here, okay, in this subheading. Then we'll understand what are the different kind of sources. Basically, you will get to know that, I mean, two kind of sources are there. First is the coherent source, and the next is what? Incoherent source. So we'll understand individually that what is this coherent and incoherent sources, and we'll dive deep in this. I mean, what are the different examples? Okay. Next is this superposition of the light waves. We'll understand this topic also. Okay. And in the last but not the least, this is what Young's double slit experiment we'll see at the end. In the end, we'll see. Okay. Young's double slit experiment. So it will start with a single slit, and then we'll end on this, that is double slit. Okay. I told you slit meanings what? See, I'll explain all the things. All the things will be explained in the class. But for now, understand like this. It is, suppose you're having a cardboard. In a cardboard, suppose you do a little kind of pinhole, or a hole which is having very less or very less magnitude width. Okay. In the terms of like micrometer or millimeter. So we'll call this kind of structure as slit. Okay. It's fine. So let us see the overview now. Let us go through the introduction to interference. So we are on the interference topic now. Okay. So see, definition says this, but let us see the picture. Before the definitions comes the practical thing. Before the theory comes what? Experiment. Okay. So first we'll start with this animation as an experiment. We'll observe something, and then we'll conclude that on the definition. Via definition, we'll do conclusion. That's fine. Okay. So I'm launching this animation. Please focus carefully. Don't miss any of the thing here. Okay. Here we go. So I hope you're observing it. What the observation is. Let us switch back. So see, initially, the source of light, this one is on, just this one is on. Now this S1, suppose this is S1 and S2. I'm removing it, hold on. See, initially this S2 is on. Now suddenly S1 is also on, okay, switched on. So what happens? There is a mixing up of two of the wavefronts. You can see the pattern, it looks good. Right? The two wavefronts, which are basically, see, if you see in 3D, these are spherical. But now, since we can see on the slide just XY plane, so this is 2D. So you can see here when this 2D wave, two wavefronts are mixed up like this, how the pattern is made. I hope you like this observation. Okay, let us see one more time. See, this is a screen here. This is what? This straight line here. This white color kind of thing. This is screen. So see what happens on the screen. This is a screen here. Okay, this white. So you can see this. The bands here appearing on the screen. This complete is a screen. Okay. Okay, let me mark the points here first for all of you. So this is source S1 say. This is source S2 say. And there is a screen which is say at a distance D from the sources. Okay. And between these sources, there is a gap of small d. Got it? This is complete apparatus here. So this is our experimental apparatus. Okay. Let me show you again there. So this is a source S1 of light. Okay, this is a source S2 of light. If you see on these slides, it will show you what? It will show you the circular kind of figures here, wavefronts here. But in the 3D, these will show you the spherical wavefronts. Remember it, okay? And these two sources are at a distance small d, and the screen is kept from these sources at a distance capital D here. This complete is nothing but the screen. Okay. So if I switch on it, we can understand, you can see this. This is a screen here. So when these two sources are switched on after a few seconds, okay, after the first is switched on, you can see the pattern is made. And this pattern, when is observed or taken on the screen, shows you this kind of bands there. What are these bands? This is black band, dark band. This is bright band. So from this, we can conclude through this experiment, remember this process is known as interference. A result is what? Result is on the screen. That is, we get the alternate dark and bright bands on the screen. Remember it, okay? What we are getting? We are getting alternate dark and bright bands there. Okay? So see, let us see the definition now. The phenomenon of one wave interference, no, we see don't interfere, okay? It's the same thing, but it's interfering here, okay? The phenomenon of when one wave interfering with the another wave. So there is interference, you can see on the screen, no? What is happening? See this. Isko switch on kiya jab experiment ko. You can see here. The wave from this source is interfering. I mean the wave fronts, the continuous wave fronts which are generated from the source S1 are interfering with the continuous wave fronts which have been generated by the source S2. And the pattern which is observed by us, we can conclude this on the screen. We can see this. These are what? Alternate dark and bright bands. See, the YouTube link is available. Just click on the YouTube. Okay, the link is available there. Okay, you can reply on the chat box. Like, if you want the link, it's available on the YouTube. Okay, I'll send the link after the class in the WhatsApp group. Is it fine, sir? I'll send the link. Okay. Okay. So we were here. Yes. Definition is this. You've already seen that the phenomenon of the interfering or the interference of one wave with the another, okay, resulting in the redistribution of energy. The energy is redistributed. What does it mean? I mean, that can only be seen by the alternate dark and bright bands on what? On the screen taken, okay? And the space around the two sources of disturbance is called interference of waves, okay? So here, the interference between the two or more light waves is just an addition of or the superposition process, which results in a new wave pattern. So it is similar to the 11th class waves, which we have studied. What is it? It's like this. Suppose a wave coming and superposing with this. This is superposition. So if these are very symmetric at all the points, we'll get a new wave which is having very big amplitude. Is it fine? Anna? But if one wave is like this and other wave is like opposite to it, if these two waves are interfering, no, we'll don't get the superposition like this. We maybe get the blank thing. So this gives you the constructive, this gives you the destructive, which you will study in the next class. Okay. So a little bit of the overview. We'll see in the next class the conditions for interference. These are the conditions. We'll see coherent and non-coherent sources, incoherent, sorry. We'll understand about, we'll go deep in this incoherent and coherent, how they look. Okay. And then we'll study about the constructive. We'll solve some numericals also. And we'll derive the equation. We'll understand the theory of interference and the superposition equations. We'll add both of the individual equations. We'll come to one equation. And at the end, we'll see the constructive conditions and the destructive conditions. Okay. So that is all about today's class, students. If you are facing any doubt, please reply in the chat box. Okay. Otherwise, I think it's fine. If you're facing any doubt, please reply in the chat box. Okay. Otherwise, I'm going to end the class now. The time is up. Please reply and do reply in the chat box, please. Please do reply in the chat box. Any doubt? Okay, doubt related to the wave optics or doubt if you're having some other chapter. Maybe you have practiced some questions. If anybody want to ask the questions based on, say, mechanics also, then also you are like appreciated. Okay, no issues. No doubt, JNV Khorda students. Okay, that's good then. If you're having no doubt, that's fine. I mean, you have practiced a lot, I hope. Okay. If there is no doubt, then that's good. Okay, one thing you understand, practice and numericals from HCV, Harish Chandra Verma. Okay, the concept of physics. That book is really good for applications. Is it fine? Okay. So bye bye all the YouTube students. I'm ending the class here. So here we go. I'm stopping the live streaming.